Okay, now I made a truly nightmarish number of errors when we did this in class. And I alluded to those errors in the preceding video. I'm going to do this thing more briefly and not allude to those errors. So I'll pretend that I did it right the first time. Okay, we have the function f equal e to the x cosine of xy. The gradient of f, as you can check, is this. We are supposed to integrate the gradient around the unit circle going counterclockwise. Now, I messed up. I wrote a clockwise parameterization. So we do have an error here already, but it's going to turn out, since this is a gradient function, that the integral of del f dot r dr is going to be 0 anyway. So in one sense it's a harmless error. In another sense it gives me a good reason to point out that, you got to be careful how you parameterize this, okay? Okay, so the unit circle we parameterize as r equals sine ti plus cosine tj. Now if it had done sine ti minus cosine tj or negative sine ti plus cosine tj, we would have gone in the clockwise direction. Or if I'd have switched the sine and the cosine so they both are positive, we would have gone in the counterclockwise direction as we were supposed to. We don't, but you can check and be sure that this parameterization, which you should be very familiar with by now, does at least give you the unit circle. So now we have a function and a parameterization, and we want to do the integral of that function dotted with the differential of that parameterization, the dr. Okay, well, the dr, you can easily, again, without going into detail, verify the derivative of the sine is a cosine, the derivative of the cosine is a negative sine, dr is a differential, so we're going to have to put a dt out here for reasons that you should understand more deeply than that simple reference. And that's what we have. Okay, now we've parameterized our dr in terms of t, so we really want to parameterize del f in terms of t. Okay, if we use the x of t functions as specified in our description, in our parameterization of the curve, then we're guaranteed that these functions, that the del f functions, these expressions, will be evaluated on that curve. So we're going to plug in sine t for every x, cosine t for every y, and this is what we're going to get. Okay, now I've written the del f dot dr here without doing those substitutions, and then I've written it out here having done the dot product with the substitutions. It's just a clerical process, which is something that I've shown myself to be not reliable on. So you be reliable, write this out clerically. You should verify. I believe this is now correct. Okay, now the problem with this is we have things like cosine of sine of t, cosine t, and the sine of t, cosine t. Those just really aren't things that we want to have to deal with integrating. I've got some ideas how they might be integrated, but I'm not at all confident that I could integrate them. The best I can do is hope for symmetries that'll show us on the unit circle you got a lot of symmetry. I hope for some symmetries in these expressions that will allow us to eliminate some of that. Also, I'll note that I have what was I going to note? I was going to note that I have some things that might cancel out. They don't. If I multiply this cosine by this cosine, I have a cosine squared. This sine times this sine gives me a sine squared, times this sine gives me a sine squared, so I have a cosine squared and a sine squared, both with negative signs, on the e to the sine t term, e to the sine t times the sine of sine t cosine t. I don't know if that's going to help. And over here, I have something that's probably going to help no more than that does. But there are things that we could look at, and again, symmetries. We're not going to worry about that. Okay, what I'm going to say is that that looks really bad. Maybe it's not as bad as it looks, maybe it is, but at this point, rather than trying to deal with that, I don't see anything that'll obviously cancel out. I have to go back and do my bookkeeping. I'm going to say this is a line integral around a closed curve. So let's translate it to an area integral using Green's theorem. Well, here's what we're integrating with Green's theorem, just to review for you. You should know this, but f dot dr is pi plus qj dotted with, you probably can't read the dxi plus dyj, but that's what I attempted to write there. We're getting kind of small and the chalk is a little clumsy. That's even worse. But anyhow, we end up with the integral of p dx plus q dy. Now I should have parentheses around that, but of course I just obliterated part of my p. Oh well. Now, we have this integral, and we know that this integral over a closed curve, assuming the interior of the curve doesn't contain any points where the p and q functions aren't defined, is going to be equal to the double integral of qx minus py, for reasons that we worked out in some detail in a numerical example when we first looked at Green's theorem. So you should be pretty well familiar with at least the idea that this happens and some idea of why, and hopefully you understand all the ideas, as well as the symbolic presentation in your book. In any case, we do this. Well, q is whatever we multiply by j, p is whatever is multiplied by I in our del f function. So here's our p function, all this. Here's our q function. Okay, our qx will be the x derivative of this, and that's going to be this. We'll have a product rule because we have an x here and an x here, as well as an x here. So I think actually the negative qx I wrote here. And the py, the y derivative of this, will have also 3 terms, and I'm not seeing 3 terms. So I'm getting a little insecure about this. Did I leave something off? Never mind. This has only 1 term, so this is the qx. Which has only 2 terms. I was looking at it wrong. And here's our py. qx minus py. When we do this, and you can check out the partial derivatives, this term and this term are going to be opposites. This is a negative whatever it is, and this is a negative whatever it is, but inside another negative. So these two are going to subtract off, and these two subtract off, leaving it just this, which leaves us just this integral. This integral we can show to be 0 without actually having to do the integration, but the integration isn't that bad. Just use some integration by parts, maybe some substitution, and that's not a difficult integral to evaluate, and I believe that integral will give you 0. We'll take a closer look at that using a little bit of symmetry shortly. Now we also want to integrate around this closed curve, the unit square, in the clockwise direction. So we'll do that next.